Hello everyone. Let's find out an expression for fringe width in case of Young's double slit experiment. Understand this. Let's take a case where there is a screen. Let's call this as the screen, and then there are two slits. This means narrow opening. Let's consider two slits. Let us call the slits as S1 and this slit as S2. So slit here is called S1 and this S2, and there is a source of light. It is called as S. Now we can have an extended source and then we can confine it with the help of a opaque material, or we can place a source here also. So S here means a source of light. The distance between S1 and S and SS2 is same. Let's take the center of the slits as a point, and let's mark a point which is exactly opposite to this center. Let's call that point as point O. Now let's find out at a given point P. So let's find out whether the point P would have a bright band or a dark band. Understand this. Let's first consider the distance between S1 and S2 as some d. So small d is the distance between the two slits, or it's the distance between the center of the two slits. It's called as d. And also let the distance between the slit and the screen be capital D. So these are general terms used in almost every book. So we first find out whether the point P contains a bright band or a dark band. Let's take the distance from P to O as some x suffix n. Also, let's mark 2 points which are exactly opposite to the two slits. Let's call this point as a point M, and a point exactly opposite to S2 as a point N. Keep in mind that the two slits are equidistant, and also distance from here would be half of it. Yes, something of this kind. So that the distance between M to O is half of D, and also distance between O to N is half of D, which is D by 2. So this distance is D by 2, and also this distance is D by 2. Let's find out what is at the point P. Whether the point P is a bright band or dark band depends on the path difference of the waves traveling from S1 and S2. As seen in the diagram, the waves from S2 travel a greater distance. So if we drop a perpendicular from S1 onto S2P, let us call this as some point J. Now this distance S1P is same as JP. So distance is to J. This distance here is the extra distance traveled by the wave from S2, and this is called as path difference. Let's find out what is the path difference and what is xn first. To understand this, we need to find what is S2P minus S1P. That's called as the path difference. We can't directly measure S1P and S2P, so here we will use some geometrical considerations. First, from triangle S2PN. So it's like this. The triangle is of this form. This is the point S, this is the point N, and this is the point P. The distance from S to N would be capital D, the distance between screen and the slits, and Pn would be PO plus ON. PO is xn and ON is d by 2. So this becomes xn plus d by 2. Now also the angle made here is 90 degrees because we're drawing a normal to the screen. Now from this triangle, S2P the whole square is equal to, it will be xn plus d by 2 the whole square plus capital D square. This is called the Pythagoras theorem. To expand this, then S2P the whole square is equal to xn square plus d square by 4 plus 2 times xn d by 2 plus capital D square. Now from here this 2 gets cancelled. Therefore what we get from here is S2P the whole square is equal to xn square plus d square by 4 plus xn d. Let's call it as 1. Similarly, if we look at triangle S1MP, so we'll take triangle. From triangle S1MP, we get a triangle of this kind. This is point S1, this is point M, this is point D. Distance between S1 and M is same as capital D, and then distance from point P to point M would be PO minus OM, because you want only PM. You can say PM is nothing but PO, that is this whole distance minus this distance, is equal to xn minus d by 2. Let's expand this again using Pythagoras theorem. Then S1P the whole square is equal to xn minus d by 2 the whole square plus capital D square is equal to xn square plus d square by 4 minus 2 times xn d by 2 capital D square. From here again 2 gets cancelled. Therefore what remains is that S1P the whole square is equal to xn square plus d square by 4 minus xn into d plus capital D the whole square. Let's call this as 2. Our aim is to find S2P minus S1P. So let's take difference of these two. That is 1 minus 2. Then what we get would be is equal to S2P the whole square minus S1P the whole square, that is equal to the left hand term. Right hand would be xn square plus d square plus small d square by 4 plus xn into d minus the whole thing minus. So if you open the bracket, it becomes minus xn square minus d square by 4 minus capital D square. It becomes minus of minus this term, it becomes plus of xn into d. So minus of minus is plus. This term gets cancelled, this gets cancelled, this gets cancelled. Finally what remains is S2P the whole square minus S1P the whole square is equal to, it will be this plus this, that will be 2 times xn into d. But what we wanted is S2P minus S1P. Now recall that a square minus b square is equal to a plus b into a minus b. So we can write this as S2P minus S1P, that is a minus b into S2P plus S1P is equal to 2 times xn d. We'll bring this term down here. Therefore finally what we get is S2P minus S1P is equal to 2 times xn d by S1p plus S2p, but this term on the left hand side is the path difference. Therefore, delta x is equal to 2 times xnd by S1p plus S2p, but we don't know what is S1p and S2p. In the diagram, if you look at it, very far distances, that is, if the distance between two slits is very small, if it's very small distance, think of the screen very far away. The screen is somewhere like this. Think of this as a screen. Let's draw this dark one as the screen somewhere here like this. Then what happens is, if you look at the two light rays from S1p and S2p, these are almost like parallel lines. Think of a case where the screen is very far away. In that case, lines or the rays from S1p and S2p travel almost the same distance, or geometrically S1p is same as S2p. We cannot draw beyond this in the screen, but think of a very far away point. The more far away the point is, S1p and S2p become almost parallel. In that case, S1p and S2p would be almost same as capital D. Therefore, for a very large distance, that is, for large distance of the screen, in other words, it means that D is very much less than capital D. In that case, S1p is almost same as S2p, that is same as capital D. Therefore, what we get is the path difference is equal to 2 times xn small d by 2d. From here, 2 gets cancelled. Finally, what we get is the path difference is equal to xn d by capital D. This is what is the path difference. Now, we need to find out whether the point P is a bright band or dark band. We learned in theory class that for constructive interference, it means that it's a bright band. In that case, the path difference is equal to n into lambda, where n is equal to 0, s minus 1, s minus 2, etc. Putting it here, and what we get would be delta x, which is n into lambda is equal to xn d by d. Therefore, xn is equal to n lambda capital D by small d. So this is the expression for xn in case of a bright band. Let's take case 2 for destructive interference, which means it is a dark band. In that case, what we get is the path difference is equal to 2n minus 1 lambda by 2. Again here n is equal to s minus 1, s minus 2, etc. So putting it back in expression, what we get would be, that is, recall what is delta x. So from here, 2n minus 1 lambda by 2 is equal to xn d by capital D. Therefore, what we get from here is xn is equal to 2n minus 1 lambda d by 2d. This is the expression for dark band. Now it means that here xn means it is the distance of the nth band. For example, if you look at this point P, suppose at the point P, think that we get a bright band. So xn would mean distance from the center bright band to this point. So it's from center to center. That's called as xn. Understand this? Let's take a case where, let's take a case where the wavelength is 6000 angstrom, and capital D is 1 meter and small d is 1 millimeter. Observe that small d is very, very small compared to capital D. In this case, what would we get? When you put it back here, then what we get is, put n as 1. I called as x1 for the bright band. That is equal to n is 1, lambda 6000, which is 6 into 10 power minus 7, and d is 1 and small d is 10 power minus 3, which means it becomes 6 into 10 power minus 4 meter. Which means at this distance of 6 into 10 power minus 4 meter from the center, we get a bright band. If you put it here, then x1 for dark band would be n is 1, it becomes 1, becomes lambda d by 2d, that will be half of this, that becomes 3 into 10 power minus 4 meter, which means, go back and see it, the distance of 3 into 10 power minus 4 meter. So from here, from the center, if you travel distance of 3 into 10 power minus 4 meter, we get the first dark band. Similarly, if we travel distance of 6 into 10 power minus 4 meter, we get a bright band. So somewhere here, distance between this center would be 6 into 10 power minus 4 meter. So that's the meaning of this equations. So as you see, we get the first dark band and bright band, and then keeps on going. Our aim is here to find the fringe width. So to find the fringe width, let's define what is fringe width. As seen earlier, fringe width is called as beta. It was defined as the distance between two consecutive bright or dark bands. Understand this. Let this be the center of the bright band, and then we'll take certain bands here. I'll just draw a bigger bands, or rather thicker bands. Think of this as a bright band, and then a bright band here, and then a bright band here, and then a bright band here. There are bands below this also. Think of this as bright. It's not been drawn as bright here, but think of these as the bright bands. Suppose if this is the central bright band, so the center of it passes through this one. So this is the central bright band, like this. Let's take this as the second bright band. This is the third bright band. The distance from here to here would be, center of this would be x2 for bright, and from here it will be x3 for bright. Now by definition of fringe width means it is distance between any two consecutive bright or dark bands, which means it will be this distance. This will be the fringe width. Keep in mind that the distance is drawn from center to center. That's called as fringe width. To generalize this, instead of calling it a second or third band, suppose if this is the nth band, think of this as the nth band. This would be n plus 1th band. If this is second, this will be third band. That's the meaning of it. So the distance from this center to this center, center of this to the center of this, is called as xn. Distance of this center to this center, center of this band, this will be called as x n plus 1. It will be x n plus 1. Therefore, from this case, beta will be equal to, it will be x of n plus 1 for bright band minus x of n for the bright band. We can use same argument for dark band also, but here we'll take the bright band. Now recall that xn for bright band is given here as n lambda d by small d. So this becomes beta is equal to, it is n plus 1 now because the band here is n plus 1 the band, lambda d by small d minus, it will be n lambda d by small d. If we open the bracket here, then it becomes n lambda d by small d plus lambda capital D by small d minus n lambda d by small d. From here this gets cancelled. Therefore what we get is that beta is equal to lambda d by d. So this is the required expression for fringe width. Now observe carefully that for a given condition beta remains a constant because it depends on lambda, which is a constant for a given condition, capital D and small d. So fringe width in case of interference remains a constant. This is a fringe width when an object is placed in, or when the slits and screen are placed in air. Now let's find out what is the fringe width when the whole system is placed in some other medium. Imagine that the entire apparatus, that is the two slits and the screen, are placed in some other medium. In that case, let us call the fringe width as beta medium. Now when the whole apparatus is placed in some other medium, or if the distance between the slits and the screen is filled with some medium, then lambda will change. So in this case beta in this medium is given by lambda for medium capital D by small d, because capital D and small d remain same, they will not change. Therefore we need to express this beta in medium in terms of beta in air. To do that, let's try to connect lambda for a given medium in terms of its refractive index. Recall that refractive index is defined as the ratio of speed of light in free space by v. But here, where v is the speed of light in that medium, but here what we want is to express n in terms of lambda. So we can write c as frequency into lambda in free space by frequency into lambda in the medium. The lambda here indicates lambda of the, or wavelength of the light in free space. Therefore n is equal to lambda by lambda in the medium, or this implies lambda in a medium is equal to lambda by n. Putting it back here, beta in any medium is equal to lambda for the medium, which is lambda by n capital D by small d. But this term, this factor here is nothing but beta in free space. Therefore what I get is beta in a medium, that is fringe width in presence of a medium, is equal to beta in free space by n. So this is the expression for fringe width presence of another medium.